And we'll change microphones, but it's a pleasure to welcome Giovanni, who will be talking about base not naives, and he starts the fingerprinting part of this session. Now, his paper has the distinction that it is, I think, the only paper this year that is from one single author, so we know that it's all his work and, you know, all of that. Well done.
Right. Well, thanks, George, for the introduction, and good morning, everyone. So I'm Giovanni Cherubin, PhD at Royal Holloway, University of London, and I'm going to talk about a method to evaluate the security of website fingerprinting defenses. Now, website fingerprinting attacks have been around for more than a decade now, and there has been this massive arms race between new attacks and new defenses, and there are two clear issues concerning defenses. First of all, well, they are typically difficult to design on the top of existing systems or existing protocols. And secondly, once we have a defense, well, there is no framework, no generic framework to actually evaluate its security or to quantify its security in a provable manner. So the method I'm going to introduce is going to give us security guarantees for any website fingerprinting defense with respect to a feature set, as I will shortly explain. And it will do so by considering the defense as a black box. And this should give great freedom to designing, actually, defenses. So let me spend a few words about website fingerprinting. So we consider a victim who is browsing some web page over an encrypted tunnel. Now, this tunnel could be a VPN, it could be Tor, more likely. What is important here is that the traffic is encrypted and that the IP address of the web server is hidden locally. And the adversary we consider is a local passive eavesdropper who looks at all this encrypted traffic. And the goal of this adversary is to predict which web page the victim is viewing. So as I said, the IP address of the web server is hidden, and we assume, well, that the adversary cannot decrypt packets. So essentially, the only information that the adversary can access is time, size, and direction of these encrypted packets. And we call a sequence of these triplets a packet sequence. So a website fingerprinting attack is made of two choices. The adversary first has to choose a set of high-level descriptions of the traffic. And this is what we call features. So an example of feature is the total communication time. That is how long it takes to download a web page. And you can see that this feature allows to discriminate between lightweight websites and very heavy ones, right? Then the adversary has to choose a classifier. Now, a classifier is just an algorithm that can be trained on some network data that the adversary collected in an offline phase just by loading web pages many times. And this classifier can be used to predict the web page corresponding to some new traffic. Now, the method I'm going to present will give us security bounds for any possible classifier the adversary can use. And it will be fixed. It will be for a fixed feature set. But then I will show that actually this is not bad news. So website fingerprinting defenses, you can imagine them as adding packets, morphing packets within some packet sequence, OK? So let's try to think about how we can prove their security. And in 2014, Tai et al. Used a method to which I will refer as the lookup table approach to demonstrate the security of a defense they were proposing, that's Tamarov. Now, in this method, they considered an idealized adversary who knows exactly what kind of packet sequences each web page can produce. In other words, he can create a lookup table where, given some packet sequence, he knows exactly which are the web pages that might have produced it. And of course, this adversary will only commit an error when there is more than one web page corresponding to the same packet sequence. And we can estimate security bounds for this adversary. We can estimate his error just by counting the collisions within this lookup table. Now, unfortunately, this method has a few drawbacks. First of all, it needs to be, when designing a defense, we need to do so by keeping these principles in mind. In other words, this method needs to be crafted around the defense being evaluated. And this is actually quite a constraint when trying to design defenses on the top of other systems. And secondly, this method is highly affected by noise, which means, OK, let me give you an example. Consider two packet sequences that are almost exactly the same, apart from one packet which arrived a few milliseconds later. Well, in that case, the adversary will be able to distinguish, because there is no notion of distance metric in this approach. And thus, we will only have underestimates of defenses security. And for the same reason of noise, well, this method can only be applied to deterministic defenses. OK, so let's sort of take a step back and think about what it means to distinguish two web pages. And let's do so just by considering one single feature, that is total communication time, OK? Now, the total communication time, given some lightweight web page, such as startpage.com, will have some probability distribution, OK? And given some other website, say freeimages.com, which is a bit heavier, it will have some other probability distribution, OK? Now, assume for a moment that these are actually the one plotted here were the correct distribution, were the real distributions of data. Well, in this case, if this was the case, the best strategy to distinguish the two web pages would actually be predicting according to these distributions. And the smallest error we would achieve is the red area you see here. Now, it turns out this is actually something well known. This area has a name, and it's called the Bayes error. So the Bayes error is the error of this idealized Bayes classifier, which knows the real distribution of data, OK? And I want to remark that this bound is intrinsic in the distribution of data, is intrinsic in our data. And thus it holds for any classifier, even computationally unbounded. Now, of course, in real world, we do not know the real distribution of data. Otherwise, machine learning would be solved. And thus, we don't know the real Bayes error. However, there are ways to estimate it. So let's go back to the problem of website fingerprinting. We consider some adversary using a certain feature set, phi, and training a classifier f. Now, we evaluate this classifier with its probability of error. That's Rf, OK? And from what we have seen in the previous slide, well, the probability of error for any classifier is lower bounded by the Bayes error, which we don't know. And now it would be nice to find some lower bound of this. And it turns out that a nice result by Cover and Hart from '67 shows that this weird expression, which is something we can estimate in practice, lower bounds the Bayes error and thus the error of any classifier. Now, let me walk you through this expression. So we need to know the number of websites being classified, the number of unique websites, that is L. And then we need to have a data set, okay, of network traces, of defended network traces. And we need to run the nearest neighbor classifier on this data set to predict its error. And that's exactly this RNN. And we know that asymptotically, this this asymptotically as the size of this data set we have available increases, well, this result will hold. Now, in the paper, well, as I said, this result is asymptotic. And in the paper, you can find details about how we can heuristically, sorry, I jumped, how we can heuristically evaluate convergence of this bound. So we have an error bound, and we may need something more, because an error bound on its own does not tell us much about the setting. In a 3 classes classification setting, that is, the adversary has to pick between 3 websites, well, by random guessing, this would be his error. In a 2 classes classification, he would have a much better, much smaller error, just by random guessing, which is why I propose this privacy parameter epsilon, which normalizes the error bound as we computed in the previous slide by the error of random guessing. And in the paper, you can find details about how this is related to the cryptographic concept of advantage with respect to random guessing. Right, so this slide presents the privacy of many well-known defenses. Now, epsilon, the privacy parameter, takes value 1 for a perfectly private defense. So what you can see here are defenses essentially listed in increasing, in order of increasing privacy. And I think the takeaway of this slide is that it is actually possible with this method to in practice, to balance trade-offs between privacy and overheads, maybe also taking into account engineering difficulties. Okay, so there is just one last question we need to answer. Does it make sense at all to have a privacy metric which depends on a set of features? Now recall that a website fingerprinting attack is made of a choice. It can be improved by improving feature sets or classifiers. And what you're seeing here is the evolution of feature set since 2006. So each color represents a different defense, and each point for each attack represents the smallest error achievable with that specific feature set. And, well, website fingerprinting attacks did improve a lot in the past years. However, as you can see here, their feature set did not improve much, which means we were able to improve classifiers, but not as much feature set. And this sort of leads to think that actually improving features is very hard, and which sort of justifies a privacy metric depending on features, and also leads us to think that maybe improving features is the next big direction in website fingerprinting. So to conclude, great. I propose this method, this black box method, to evaluate the security of any website fingerprinting defense with respect to a set of features. Now, I've shown why it makes sense to actually make this assumption. But of course, the next natural research question is, can we actually produce some bounds that are independent of these features? Then a second research question is, can we try other base error estimates? And you can find more on the paper about this. And finally, I would like to stress that this method, this technique, is not bound to the problem of website fingerprinting. Whenever an adversary has to distinguish between some scenarios, and to do so has to train on some data, well, we can immediately collect the data set and estimate these error bounds. And so I can see this applied in traffic analysis, in side channel attacks. This morning, the first presentation, for example, was trying to distinguish between real Skype traffic and Skype traffic with some cover channel. Well, we may actually be able to use this to derive security bounds for that. And note that if for some of these attacks, the adversary had only access to some limited information, so it didn't have to extract features, well, we would immediately have these epsilon privacy guarantees. So thanks a lot for listening, and I'll be looking forward to your questions.
Okay, great. Thank you very much. So I get to ask the first question. So I'm very